Okay, this is going to be the last part of Unit 5 on ocean sediments. This is the cosmogenous sediment as well as wrapping up the unit. Cosmologist was from space, so these are going to be actually asteroids or comet remains that actually make it through our atmosphere, splashing down into the ocean, probably pulverized into lots of different pieces. So they're extraterrestrial fragments. They come in a couple of different forms. They're called glassy tektites. Tektites are just small little objects that are actually coming from sediment and coming from space. They're also called ferronickel micrometeorites. So you can see them in this container. If you ever go to Asteroid uh, Canyon, it's not called Asteroid Canyon. If you ever go to the asteroid remnants right outside Flagstaff, Arizona, Barringer Crater, you can actually, they'll take you out there and they'll take a magnet over to an ant hill where the ants are bringing up sediments very similar to that ant farm that's in our classroom. And they actually take the magnet and they go over it and they pull up these little iron magnet meteorites, micrometeorites, itty bitty, teeny tiny, itsy bitsy things. They're usually found in deep sediment where other sediments accumulate very slowly. These do not accumulate in very large concentrations, so when any time you get a terrestrial or you get biological or hydrogenous sediments forming very quickly, these don't show up even though they are there. So this usually is forming only where the other sediments are accumulating, either not accumulating or accumulating very slowly. The way we get those is we get an asteroid. This is supposed to be like the asteroid that hit 65 million years ago for the KT boundary, which you can see is going to be located right here, where we have Cretaceous, which is going to be the K, and the T, the tertiary sediments. This is the KT boundary. I've shown with Iridium, which is a material that's not found very prominently here on the planet, but it is found in high concentrations in asteroids. So an asteroid came in, and the neat thing about this asteroid is it actually touched underneath the ocean. This is the Yucatan Peninsula. It touched the surface of the ocean floor, going through the entire ocean, sticking up through the entire atmosphere, and that's still out in space to give you some idea. And of course, it was traveling at 30,000 miles an hour, so it didn't take very long to hit. KT meteorite crater, Yucatan Peninsula. There's a 30-mile crater, most of which is underneath the ocean. The stuff above land, of course, vegetation and other things have hidden it. It wasn't until we started looking for oil and things out in the ocean, the Gulf of Mexico, that we actually saw these concentric circles showing you a meteor crater. Tektites and spheroids, these are found in marine sediments throughout the world, but in very, very, very small concentrations. You also find what's called shocked quartz. Shocked quartz actually happens when we take quartz and we subject it to very quick, high pressure, high temperature, and it actually takes the quartz and it polarizes it. I'll show you that on the next slide. And we also have this worldwide iridium layer. And again, iridium is not found in high concentrations of terrestrial rock, earth rocks, but is found in high concentrations in space trash, asteroids and comets. This is a picture of tektites and spheroids. These are actually going to be very Earth-like coloration, but if you take a look at them in terms of the shape, they're like oolites, but they're actually made of different types of material. This is shocked quartz. This is the KT boundary, and you can actually see this shocked quartz. It gets these striations in them, which you can only see with high magnification, but it actually is showing you high temperature, high pressure quartz. It's been shocked. Mixtures of sediments. Most places on this planet, and even if you look at the picture on the front, and I'll show you another picture of this later on, most of the places, when we actually say they're abyssal clays, or they're going to be siliceous oozes, or they're going to be calcareous oozes, or they're going to be lithogenous or pterogenous sediments. Most of the time we find all types of sediments in there, just this is the primary type. You can actually see we've got green areas and blue areas and dark green areas, as well as this orangish pink area. So most marine sediments are mixtures of all four types. I'm going to put the fourth one in there, Cosmogenous. Cosmogenous makes up a very small, way less than 1%, probably less than 1/100%, maybe even 1,000th of a% of most sediments. Usually one sediment type is dominant, and that's what you see in this picture. The Arctic Ocean is almost all lithogenous, land-based sediment. Examples, we have neritic or beach type sediments close to coastlines, mainly lithogenous along with seashell fragments. We have coarse calcareous rubble along with quartz. So we have terrogenous, lithogenous along with biogenous, and biogenous with lithogenous. Remember, we do get this calcium carbonate compensation depth, the CCD, where we get calcium carbonate ooze as long as it's underneath that 4,500 meter depth. That gets lower and lower up by the poles because we get higher concentration of life. So the high production actually is pulling the calcium carbonate back into shells. So it's not really in the ocean to precipitate on the land, but it does make sort of like a marine environment. Calcareous ooze most common in deep ocean floor, less than 4,500 meters, and that's due again to the CCD. Abyssal clays most common in deep ocean. Once the calcium carbonate's out, we usually get the abyssal clays, very small particles coming off the ocean or off the continental coastline. The sand falls off first, the silt falls off next, and then this clay type material, very flat sediment, which is one of the last ones to settle out because of its shape. Distribution of marine sediments. Here's that larger picture I told you about. Understanding that even when the abyssal clay is out there, we do get calcareous oozes if the altitude of the seamounts or the mid-ocean ridges is less than 4,500 meters. We also get terrogenous materials as well as hydrogenous materials out there. So we do get mixtures of all of them. Last slide, Unit 5. This is actually the KT boundary. Here's where we actually find that Iridium anomaly, which we find worldwide. Let's take it back. I need to go over that one more time, just a little bit more, which we do find worldwide. And what we do is we find the Cretaceous microorganisms, things that lived in the Cretaceous. Then we get the KT boundary. Then we get large ejecti area where the material got thrown up into the air and fell back down, suffocating all life. We find very, very little life, but you do find tektites, glacis, globules, all things that you actually find that would rain down after an explosion like this. This is going to be in centimeters, so you can see this is 10 centimeters, almost 20 centimeters of material. Then we get fireball fallout. Usually that's the Iridium layer. Then we get the Strangelove Ocean, where we get sediments falling down, almost no fossils whatsoever. Then we start getting new life forming, and then we get the return to normal conditions, very much like we had down here, although the critters have changed, percentages and type critters, where we get calcareous skeletons and siliceous skeletons, and we get bones of fish and other things. So that's the end of this C part. We're doing it C part, the third part of Unit 5. Thanks for stopping by.